Oh, minus f.
F is there and their average is there. So 0 must be there. Okay? Alright, so let's see that why this must be true. So that's how we can drag this ball out onto the ball of radius 0 in such a way that. And this is a condition with the if factor. If this happens, then this will happen. Okay? Now suppose that there is a ball with the radius r such that it is contained in K. There is a ball with the radius r such that it is contained in K, and I would like to show that this must be true as well actually. Okay, so I have I'm not. All right. Okay. Now, if this is the case, then this negation of the ball, okay, it's not really a negation of the ball, it's a collection of negations of f such that the distance between f and some g such that
G is equal to minus f. ये बाय डिफाइन करें सर, G is equal to minus f.
So what would be the meaning of this? So it contains the points
G from E.
Okay, so it contains minus G such that G is from the ball which contains minus G such that G is from the ball. And I know by symmetry, this is also a subset of K. Agree? This is also a subset of K. Is it making sense? Why this must be subset? Just think about it. If I take any, minus G from J, okay, from this set, then the minus of this is going to belong in BFR, but that is contained in K, so that minus G is going to be in K. And also this interesting set. So BFR minus BFR divided by 2. So that's just a symbol actually. Okay? That's just a symbol to represent a set. So set is what? Set is that it's a collection of some H plus K over 2 such that H is from BFR and K is from minus BFR. Okay, that's the set. The set of all averages of these that you can take. So by the midpoint convexity, this is also a subset of Q. Agreed? This is also a subset of Q. Now I'm going to say that this is actually your, this average is actually your P0R. This average is actually P0. Okay? Why this must be the case? So take an arbitrary element from here. Okay. So I'm saying that this guy, I claim, is a claim that this BFR minus BFR by 2 is your V01. It's equal to V0. Okay? So for that I need to show what, like, okay, containment of this side into this is trivia. Okay, it's not that difficult. The real thing is that why this must be contained with this.
Okay.
So I would say that let H is from
B
to
0 R.
R such that what? The norm of H is less than or equal, or that's what the definition is. Okay? Not less than, but strictly less than.
And E sense.
In this sense, yes. That's a norm in E.
Sahi.
Then H can be written as this actually. So I can write H as G plus. So that's, can I express H as the element of this plus this over 2? Okay. So here's the interesting thing. So G plus F minus G plus H minus G minus H divided by 2. Okay? G plus H minus G minus H. So is G plus H an element of BFR? So if I take G from BFR, so G plus H over 2 is an element in BFR. And G minus H over 2 is an element in BF minus R, and hence, you know, this guy, you know, must belong to this sequence. Okay? This completes the proof factor. Okay? Since this is contained in K, so obviously P0R is contained in K. Alright?
सर जो इसका पहला पार्ट होगा G प्लस H बाई 2 वो कंटेन होगा बॉल एफ आर में या बॉल ऑफ एफ आर डिवाइड बाई 2 में. इसका पहला पार्ट H का जब हम दोनों को सेपरेट करेंगे G प्लस H बाई 2 माइनस G माइनस H बाई 2.
Figure out for yourself, it's not difficult. Okay. Figure out for yourself. It's evident, and if you think carefully about the definition. You might ask actually once they okay. No. I must write F here. Alright. Is it fine now? Because we centered our ball at F actually. Not an arbitrary G but F. I'm sorry. This was creating the confusion. Alright, so now I'm going to prove our so-called uniform boundedness principle, and my argument is going to be this lemma and the Bayes theorem, as declared that the Bayes theorem is responsible for this beautiful result. So here's a proof of uniform boundedness principle. Okay. One side is pretty much obvious. So what was the uniform boundedness principle? That a collection of linear operators is uniformly bounded if and only if it's pointwise bounded, provided that the domain of the operators is a Banach space. The domain of the operators is Banach space. If E is a Banach space, okay, and tau is a collection of all linear operators from E into F, then this collection is uniformly bounded if and only if it is pointwise bounded. So one side we already showed that uniform boundedness implies pointwise boundedness in general, whether E is Banach space or not. Okay? But I would like to show the other side now. Okay? So in other words, let let tau be a collection of what? Pointwise bounded. Maybe the best way to say it would be that let tau be the collection of linear bounded operators from E into F actually. So it's like a pointwise bounded operators from E into F, where E is Banach space. E is Banach space. So that's a key thing that we will like to. Now consider a collection of sets. That collection of sets is Kn. I'm defining Kn. I'm going to use this lemma. So I'm defining Kn. So Kn consists of those points from E, such that, such that norm of their, norm of the images under T is less than or equal to n for all E in the collection. Okay? So Kn is what? Is a collection of all points of E such that the norm of the pointwise norm of T can be bounded by n actually, but for all T. Then we're going to talk about the Kn actually. We're going to investigate some properties about the Kn. Okay? Well, I'm going to show that essentially the union of Kn is going to give you E. Okay? So I'm going to show that Kn is symmetric and midpoint convex for every n, and its union is going to exhaust the whole of E. Okay, and hence the Bayes' theorem is going to give us, is going to basically take us to our required conclusion.
Arbitrary.
Arbitrary. What do you mean by arbitrary? Okay. Now, here's a point. So since each of T from tau is bounded, okay, so each of T from tau is bounded and hence linear as well. So it is continuous actually. So it is continuous. Okay? And using this I can show that Kn is closed in E. It's a closed subset in E. Why this must be closed? Why it must be closed? I mean, if you remember, we did this kind of exercise, this kind of question in exams actually. Did you remember that? Many of people attempted correctly. Yeah, the first mid-exam actually. Where we said that imagine I have, a collection of C's, and that's collection of C's is so we did something like that. Anyway, we can also prove that it is closed. How can I show it closed? Let's show it. How can I show it it's closed actually?
सीक्वेंस पिक करेंगे, उसके अंदर कन्वर्ट करवाएंगे.
Let's pick a sequence. So let Fn and maybe Fk, where k belongs to n, be a sequence
from Kn
from
Kn
k such that
Kn sir K sub n.
from Kn such that Fk converges to some Fn as k goes to infinity. Okay. Now we need to show that this F must also be in Kn actually. How can I show it? Now since each of this k, Fk is in Kn, so this must be true. So limit of T Fk is less than or equal to n for all k and n. Agreed?
G.
So if I take the limit on both sides, so limit k goes to infinity, T Fk, this could have been a very good exercise actually. Why am I ruminating? Okay. So if this is the case. Now since the norm is continuous and the T is continuous, so I can plug this limit inside. Okay? So since norm is continuous and T is continuous, so
TF is
using the
less than
quantity I can say that
TF is less than
Tf is less than or equal to,
hence F is in Kn.
and this implies that F must be in K, and hence Kn is closed. Okay? The next is to see, the next claim in this proposition is that to see that this whole space E can be written as the union of Kn. Kn. Why this must be the case actually? Just think about it. In other words, what does this thing is saying? That every element of E is in some Kn. Why this must be the case? So let's pick an element from E. Let F is from E actually. Okay? Then we have this collection, which is collection of linear pointwise bounded operators. Isn't it? So I would say that Tf is less than or equal to norm of Cf, okay, for all
F and E.
for all F in for all T.
T. Point
Okay. This must be the case. Alright. Now here's the question. Okay, since F is finite, so F is in E, so it's a finite quantity. So C is also a finite quantity. Then I can always find a natural number which is bigger than or equal to this. Okay. So since these both are a finite quantity, so that's a finite quantity. So this implies that I can find always a natural number such that the M such that the norm of Tf is less than or equal to. And this implies that F must be in Kn. Okay? And hence this equality. Alright? So, what we have done so far, we have E, which is a Banach space, complete. We have closed subsets of E, and we have that their union is whole E actually. So we are in the assumptions of Bayes' theorem. Are we in the assumptions of Bayes' theorem? We are in the assumptions of Bayes' theorem. So by Bayes' theorem,
ball exist
by Bayes'
theorem,
theorem,
there
exists some G in E and
natural
R positive
natural
and natural number such that
वो ball
ball
closed ball
of G centered at G with the radius R is contained
contained in K
in Kn. Okay?
ठीक है वो हो गया सही
But we just did in, the previous lemma that was about midpoint convexity, that if you have any ball that is contained in a, which is centered at G, I can translate it.
but
But
Kn
before
should be
that I need
symmetric
to show Kn must be midpoint convex actually.
and also symmetric.
Yes. So is Kn. So next we're going to show that Kn is midpoint convex. Midpoint convex and symmetric. Is it?
Yes sir. F and G pick T apply N gonna T होगा.
So if the norm of Tf is less than or equal to n and norm of G is less than or equal to, so verify it for you. It's a pretty nice and easy exercise actually. Okay, pretty nice and easy exercise. Okay. And if you take F and G, whose norm of Tf is less than or equal to m, then you take the average.
And apply T.
The applied T is going to be still less than that.
Regular inequality, natural number.
And similarly, the negation. So, both things are trivial. So, my last lemma, I can drag or translate this ball to a region F. My last lemma, B0R is contained in Kn. Okay? B0R is contained in Kn. But what is the meaning of B0R being contained in Kn actually? What would be the meaning of this? So in So what does this mean? This means that every f, okay, for which the norm of f is less than or equal to r, we have Tf less than or equal to f, right? This is what that it means actually. So if you pick an f from this ball, this must be satisfied. And for such an f, this also must be satisfied. Are you getting the point? And now, so I would like to play a little game. If I say that r times, say if I consider this actually, r times Ef. So I can take this r inside because r is a positive number. So I can take even r inside, what do you call, f. So this would be same as a t of rf. Okay? And this is less than or equal to what? N over r. N over r or n? Less than or equal to n. Can we combine all these? Yes. And this means if I divide both sides by r, the TF can be estimated by n over r, and this is true for all what? For all t in t. So see, essentially what was your task? My task was to prove that there is a number. Okay, let's not call it n, but let's call it m actually, so that we would not treat this n as an arbitrary thing. So let's call it a fixed number. So this must be m. So this must be m, and here must be m, and here must be m actually. Okay. So what does this show? This shows that the images of, okay, so image of f under the norm is always less than or equal to m over r for any t. So if this is true, just think about it. Isn't that showing that the norm of t is always less than or equal to m over r, this fixed number m over r? Agree? And I'm saying that call this as C. Give it a name, C. And norm of t is what? It's a supremum. So if this guy is less than or equal to r for all
T
f, so
tau.
it must be less than or equal to what? This f. Are you getting the point? And what does this show? So this is true. This is true for all t in tau.
So हमने
And hence we showed
point
that
wise
there is a constant which is bigger than all of the norms of the operators in T at capital, and hence tau is uniform. Yes.
हमने point wise से uniform
Yes. Tau is uniformly bounded.
वो तो trivial है. Uniform से point wise.
Yeah. So we did it already. So no need to do it.
सही हो? जो T of RF when we apply T और वो भी हम कह रहे हैं less than equal to m.
Okay.
हमारे से.
Figure out what's going on. It's a pretty simple thing.
शांति आ रहा है.
So here's a hint. I'm saying that this condition and this condition both are equivalent. Both are equivalent. I'm saying that's another way to say this. Think about it. So it'll be a good exercise. A good exercise. Okay. So that was, what do you call, first consequence of uniform boundary principle, and then even there are lots of applications of uniform boundedness principle. Okay, I'm going to do one. I'm going to leave one for you. You can read it for yourself. One of the excellent application of uniform boundedness principle is that, you know, under certain conditions, this Fourier series, okay, about which we have always heard that it's convergent, under certain condition it diverges as well. Okay. So non-convergence of Fourier series, there's a little section there, there are small calculations. I'm not going to do all these calculations. Just read this out and you will see one of the applications of this. Okay. And that's optional actually. I highly encourage you to read, but not forcing you to read at the moment. So this is section 15.3 from here. But I'd like to talk about the corollary of this result. I think a corollary is theorem in itself actually. That's a theorem due to Banach.